what's a giant ionic lattice? A giant ionic lattice is one where you have like NaCl, you have positive ions attracting negative ions,
Yeah.
and alternatingly they're all attracting each other. They're forming a crystal. So Cl ions would be attracting sodium ions would be attracting Cl ions, and this continues in 3 dimensions. So it's going to be Cl ions attracting sodium ions back again, sodium ions attracting Cl ions. So they would be forming cubic lattices where lots of positive ions and negative ions attract each other. So they only have ionic bonds. There is no intermolecular force.
Okay.
Okay, it's one interconnected structure where all ions are bonded to all other ions, all negative ions are bonded to all positive ions by ionic bonds, strong ionic bonds. Okay, so there is no intermolecular force. They're only bonds. Okay, is this clear?
Yeah.
The second structure that doesn't have intermolecular forces is it's called a giant metallic lattice. Okay, that's the other substance. Now, giant metallic lattices only have metallic bonds. What's a metallic lattice? It's a group of metal atoms, all regularly arranged. Okay, so here are a bunch of metal atoms. What do metals like to do? They like to lose electrons. So all these metal atoms, they would tend to lose electrons. They would form positive ions. Okay, metals they really like to
Yeah.
lose electrons. And where would the electrons go? The electrons would just be roaming around in the middle, in the gaps in between the atoms. Okay, so is this clear?
Yeah.
So it's going to be a giant metallic lattice of positive metal ions in a sea of free moving electrons. And they only have metallic bonds. And what's a metallic bond? A metallic bond is the electrons are acting as a glue. They are attracting the positive ions. They're all attracting the positive ions, and the positive ions are attracting the
Yeah.
electrons in return. Okay, so there's only one force of attraction present, which is a bond, and the third one is and the third one is it's called a giant covalent structure or a giant covalent lattice.
Yeah.
Achha, so it only has covalent bonds. Like diamond is one example. So if you look at diamond, it's carbons bonded to covalently bonded to other carbon atoms, which are then further bonded to other carbon atoms.
Yeah.
Okay, so all of them, and it's going to just continue. So there would be carbons bonded to other carbon atoms. So only covalent bonds are present.
Okay.
Okay, Amal, is this clear?
Yeah.
Uh, so remember all these three substances, they don't have intermolecular forces, they only have bonds. If you see
Okay.
a crystal of a salt, then it's one interconnected structure. It's a single entity. If you see a piece of metal, that's a single entity. It's all everyone is bonded to everyone else. If you see a
Okay.
diamond, all the atoms are bonded to each other. So there are no intermolecular forces. Intermolecular forces are usually present between molecules. Like you have these tiny molecules. So remember this, that simple covalent molecules have intermolecular forces.
Yeah.
I said the simple covalent molecules have intermolecular forces. For example, there would be a carbon dioxide molecule, that's a simple covalent molecule. I mean, the
Yeah.
whole structure is limited to one carbon and two oxygens, that's it. And then there's another carbon dioxide molecule flying around, there's another carbon dioxide molecule that's flying around. So there would be very weak attractive forces. I said there would be very weak attractive forces between molecules. Okay, Amal, is this clear?
Yeah.
Then these forces can be weak and they can be strong. So, Amal, what factors are dependent on what properties would change? I mean, what properties are dependent on intermolecular forces? Can you name a few?
Like the boiling point and the melting point.
Okay, so that's the first one, the melting and boiling points. They are definitely dependent on, and you pretty much know that if you have more intermolecular forces, then it would become harder to melt or boil. So melting boiling points,
Yeah. And
what else?
melting boiling points and how like I know what's the word for it, like how I think how reactive it is as well because it's less reactive if you because you can't break the bonds.
Not. I'll come to that, but that is one point, okay? But not the way that you're describing. Uh, as I'm going to talk about reactivity, but I'm going to put reactivity a bit later. Solubility depends on intermolecular forces.
Yeah.
Okay, that's one. As a, how does solubility depend on intermolecular forces? So, for example, you have certain substances that are soluble in. As whenever you talk about solubility, usually you're referring to the solubility in water.
Yeah.
In chemistry, we talk about water a lot. Why? Because water is the main medium on planet Earth. It's 70% of the Earth's surface is water. Our human body, that's all our cells. Every solution is pretty much made out of water. Plants are constantly absorbing water, so we're all surviving on water. Okay, so Earth is surviving on water. Uh, I mean, there are other solvents as well, but usually in chemistry we're not talking about them. I said so. So there's a rule about solubility that um, if you have, I'm going to discuss this in detail later on as well. I'm going to just explain that same type of forces, or I can say that, or I can simply write that. Maybe you already know this. Polar dissolves polar, and non-polar dissolves non-polar.
Yeah.
Do you know what a polar molecule is?
Yeah. I think with one part of the molecule has a like a positive charge and one part of it has like a different as a negative charge.
Okay, okay. So, for example, I have. I'm not going to go into a lot of detail. Just right now, I'm just going to talk about HCl. Cl has a slight negative charge. H has a slight positive charge. Do you know why that happens?
Um. No.
I mean, because electrons are being shared, right?
Yeah.
But one of the atom has a stronger attraction for those electrons. Like it's more electronegative. TK, do you know about electronegativity?
Yeah.
I said it has because I mean look at chlorine. Chlorine has how many protons? It has 17 protons. Look at hydrogen. Hydrogen's nucleus has one proton. So obviously one proton would not be able to attract the electrons that strongly. So the electrons are kind of closer to chlorine. Okay, is that clear?
Yeah.
I said anyway, so let's say this molecule is polar. And there's this other molecule which is also polar. Let's talk about a water molecule. It has a bent shape. And this side is negative, this side is positive. And let me draw a few more water molecules.
Yeah.
This side is negative, this side is positive. And one more HCl molecule. I said, now what's going to happen is that originally polar molecules they attract each other very, very strongly. Okay? So the H is going to be because the H has a what charge? It has a positive charge, a very slight
Yeah.
positive charge. The Cl has a very slight negative charge. Okay? So there's a slight negative charge. So the
Yeah.
positive side would attract the negative side. So there's going to be some intermolecular forces between the molecules, right? Is this clear?
Mm-hmm.
I said now to dissolve substance, you have to vigorously stir. When you stir them, the molecules are going to mix. So imagine I'm mixing them up. So this water molecule would go over here. This HCl molecule would end up over here. Okay, is this clear?
Yeah.
I said so. Water is a polar molecule as well. So the negative part of oxygen would attract the positive of HCl.
Yeah.
And the same would pretty much happen over here. For example, this HCl molecule, the negative part would attract the positive, right? Is
Yeah.
this clear? The Cl
Yeah. That's fine.
negative would attract the H positive. Okay, so they would all be attracting each other. So they're bound to mix.
Yeah.
All the molecules are going to mix with each other because they're all attracting each other. Like previously, the water was attracting water molecules, but now the water molecules can attract the HCl molecules. The HCl molecule could attract another HCl molecule, which could attract a water molecule. So they're all mixed together, right?
Yeah.
I said, but then there's another statement which is that polar does not dissolve non-polar. So polar molecules they don't does not dissolve
Oh,
non-polar
yeah.
molecules. I said why? I said non-polar molecule is the molecule where the electrons are equally shared. Like
Yeah.
you have an oxygen molecule. I mean, this oxygen would try to pull electrons. This oxygen would try to pull electrons as well. But both of
Mm-hmm.
them are going to pull electrons with an equal force, right?
Yeah.
So where would the electrons end up? They're going to remain right in the middle, right? Right in the center. Okay, Amal, is this clear?
Yeah.
So they would, I mean, no charges are going to build up. The electrons would be evenly distributed between the two oxygen atoms. So no side would be negative, no side would be positive. This is not happening, that the electrons are getting pulled towards here. Over here, the electrons would be evenly or equally spaced between the two atoms. I said, but then I
Yeah.
have an HCl molecule. And that molecule is very polar. I said, imagine that I've already mixed the oxygen molecules together with the HCl molecule. I vigorously stirred them. So,
Yeah.
so you have another HCl molecule. This is negative. This is positive. Sorry, this is negative.
Okay.
I said, so I've kind of mixed them. But tell me, which two particles would attract each other?
The positive and the negative, so the opposite charges.
Okay, so I mean, the oxygen doesn't have a charge, so oxygen is not attracting, right?
Yeah.
So the HCl particles would be attracting each other. So what would happen eventually is that all the HCl molecules, they would group together,
Yeah.
and the oxygen molecules are going to be pushed to the side.
Hmm.
Okay, is this clear?
Yeah.
And that's how layers are formed. When two liquids, they don't mix, when substances don't mix, no matter how hard you try to actually mix them, they're not going to attract each other.
Okay.
Okay, and the ones that are polar, they would attract each other, they would form a layer, which is why oil and water, they don't mix.
Yeah.
So then polar does not dissolve non-polar. The third statement about this is that
Hmm.
non-polar and non-polar are going to mix.
Yeah.
What this statement actually means is, let's say you're at a very low temperature and there's liquid oxygen
Yeah.
and there's liquid nitrogen, and I've stirred them together and I've mixed them. Now both of them are non-polar. So is there any reason for them to unmix, like to form separate layers?
No.
Because oxygen is not attracting or not strongly attracting any other particle. The nitrogen molecules are also not attracting any other molecule. So if you mix them, they're going to remain mixed. Okay, is this clear?
Yeah.
So the first one, polar dissolves polar. The reason they mix is that the polar molecules, all the polar molecules, they don't, no matter how you arrange them, they're still going to attract each other, right?
Yeah.
Polar would not dissolve non-polar. Why? Because the polar molecules would attract each other and they would form a separate layer. But non-polar and
Okay.
non-polar are going to mix. So this is just a brief idea that solubility depends on intermolecular forces. I said, now what else? Uh, any idea?
Um.
Number three could be
Maybe.
that. Hmm?
Maybe like to cut it and stuff, because some metals you can cut. So
Need cutting?
yeah.
I mean, that's state basically. Like if I mean, some of them are gases. I mean, they're not attracted to each other very strongly.
Oh, okay.
I mean, you can write that down. The state of a substance. Okay, that's obviously whether it's a solid. If the intermolecular forces are weak, so solids. If the substance is a solid,
Yeah.
that indicates strong intermolecular forces, right?
Yeah.
Vice versa, if it's a liquid, or let's say it's a gas, then that would indicate very weak intermolecular forces. So then another thing that depends on intermolecular forces is the rate of evaporation. Evaporation, and also there's a thing called the vapor. So there's a thing that's called the vapor pressure. Do you know what the vapor pressure is? Amal, any idea about vapor pressure?
No, we haven't done that before yet.
So what is evaporation? Evaporation is like boiling, right?
Yeah.
But slightly different. What's the difference between evaporation and boiling? I mean, what differences can you point out?
Um, Evaporation is when the molecules turn into gas, but like boiling is like you're just boiling the
The same thing happens.
boiling is like you yeah.
But what's the difference? Like, if something is boiling and something is evaporating, how would you identify whether something is boiling or something is evaporating?
When something's evaporating, the steam coming off of it, but if it's boiling, then it's just bubbling.
Okay, one thing is evaporation happens only on at the surface, right?
Yeah,
And evaporation happens because particles are constantly. I mean, you don't need an energy source. Particles, like if you throw water on the floor, it's going to evaporate because particles are constantly bumping into each other, and the energetic particles would
yeah,
break the intermolecular forces and they can escape as a gas from the top surface.
yeah,
Okay? So evaporation only happens at the top surface, like these particles over here. At the top, you get these particles over here.
yeah,
They might, a few of them would be very energetic, so they would kind of break the intermolecular forces, and they would overcome the attractive forces, and they would change into gaseous state, right? So that is evaporation.
yeah.
Happens only at the surface. Evaporation can be affected by temperature, not temperature. It could happen at any temperature, but it's going to be affected by temperature. It would be affected by wind. Like if you're drying clothes on a wire, it's if it's windy, they would dry up quickly. Okay.
Okay.
Acha, but boiling happens at a very fixed temperature, and when boiling is happening, the entire liquid is actually boiling, not just the surface. Okay, is this clear?
Yeah,
And for boiling, you usually need an energy source. Like it's not going to happen on its own. Evaporation happens on its own. Acha, so evaporation depends on intermolecular forces. Now I wanted to explain what vapor pressure was. Think of this as a water bottle, and there's water in the water bottle. Why don't you see water evaporating in the water bottle?
because it's in an enclosed space and it's not like heated, and like when it's in an enclosed space, so that particles can't escape.
I mean, they can't because they can't escape. I mean, the particles, the energetic particles would escape, but they have nowhere to go. So they're going to bump into the walls of the container, and when they do that, they would eventually lose energy.
Oh yeah,
I said, one second, I've actually lost the board. Uh, I said they're going to lose energy, and when they lose energy, what happens? They condense back. They fall back into liquid state. Okay, is this clear?
yeah,
So an equilibrium is established. Like every second, 100 molecules are evaporating. I mean, so there's water liquid and there's water gas over
yeah,
here.
yeah,
Acha, so every second, uh, water is changing into gaseous state, molecules are escaping, but at the same time, molecules are condensing back again. So the net effect is that you don't see a net effect. Like if there are three molecules of water vapors formed, and every second two molecules evaporate and two molecules condense back, so the net quantity of water vapors remains exactly the same. Okay, Amal, is this clear?
yeah,
So there won't be any effect on the amount of water vapors, uh, which is why you never see water evaporating in a bottle, in a closed bottle. Although
yeah,
it is evaporating, it's constantly evaporating, but it's constantly condensing back again. I say, anyways. So what is vapor pressure? So let's assume that an equilibrium has been established. What's vapor pressure? Vapor pressure is that the particles that have turned into vapor state, they would be hitting the walls of the container and they would be exerting a pressure, right? Like if you open a Pepsi bottle, there is
Yeah.
vapor pressure in it. Like particles are escaping as gaseous state, and they're hitting the walls of the container and they're exerting a pressure. So that is simply vapor pressure. Okay, is that clear what vapor pressure is?
Yeah.
So vapor pressure is it's the pressure exerted by the vapor.
Yeah.
So it's the pressure that's exerted by the vapor when it is in equilibrium with its liquid phase. So when it is in equilibrium with its
Yeah.
so when it's in equilibrium with its liquid phase, that's vapor pressure. What do you think? If intermolecular forces are weaker, would you have more vapor pressure or less vapor pressure?
If the what?
If you have weaker intermolecular forces,
Would there be less vapor pressure?
why?
Because the intermolecular forces are they're like weak. So like
Would they be,
there's not much pressure.
if the intermolecular forces are weak, would there be more evaporation or less evaporation?
Um, I think if there's a weaker intermolecular forces, there'll be less pressure.
What about evaporation? Like there's this
Yeah,
particle. I mean, there's
it'll
this.
be easy to evaporate.
Okay, so it's going to be easy to evaporate. So more particles are going to evaporate, right?
Yeah,
Because they can easily overcome the attractive forces because they're weak. And if they
yeah,
so at equilibrium, you're going to have more vapors, right?
yeah.
So if there's more vapor, would that create a greater amount of pressure or not?
No.
I mean, there's more vapor, right? So
Yeah,
these particles would go and hit the walls of the containers, and they would exert a greater force. I mean, previously you just had
mm,
three particles. Now you have like
yeah,
seven, eight particles, six particles. So now the amount of pressure that these particles are going to exert, it's going to be greater. ठीक है, Amal, is this clear?
yeah,
So more vapor would be produced,
yeah,
and there's going to be greater vapor pressure. ठीक है, there's going to be greater vapor pressure. So, anyways, what else what other factor could increase vapor pressure apart from intermolecular forces? Like if I
um
what what would happen with temperature if I let's say increase temperature? What's going to happen?
then I think the vapor pressure would increase because you're giving the particles more energy, so it bounce off the walls more.
Okay, so higher temperature, uh, two things would happen. There's going to be more evaporation because it would become easier to overcome the intermolecular forces. So
Yeah,
there's going to be more vapor, plus it's going to be more energetic as well. So not only are they going to bounce off the walls of the container in greater numbers, but they would hit the container with more force as well because they're more energetic.
yeah.
They're at higher temperature. Okay. So then another small point about this is that if you're at room temperature, the vapor pressure must exceed it must exceed the atmospheric pressure
Yeah.
for evaporation to happen. For evaporation to happen. What does this mean? Now we want evaporation to happen. What's going to happen is, like, let's say you have an open container now. I said, let's say you have an open container, and this time there's liquid water, and we want that water to evaporate. So these are all these molecules. I'm not heating it. Okay, so liquid molecules. Eventually, 3, 4 particles would evaporate, right? Now,
Yeah.
for evaporation to happen, I don't want these particles to condense back. Like, I don't want them to stay there. I don't want them to lose energy and fall back into liquid state. What I want them to do is, I want them to escape and go somewhere else. Right? Is this clear?
Yeah.
I said, because if they stay there, there are chances that they might lose energy and they might fall back into the container. Okay? So is this clear? This is evaporation. I said, what do you think is stopping them from going somewhere? Amal, any idea?
Yeah.
Any idea what's stopping them from going somewhere? Like, I want the particles to evaporate and disappear and go somewhere else. What is stopping?
Yeah.
So, what is stopping them from going somewhere else? Like,
It's
why?
the container, like where it is
But the
contained.
but the container is now open.
Then I think it's just the sides of the wall because they're all trying to get out at the same time because the pressure's just been
They,
nearly.
remember, although you can't see it, but there's an atmosphere. There's air around it, and,
Yeah.
and there are lots and lots of air particles around it, surrounding it completely. And these air molecules are trying to keep them in. They're exerting a pressure. So it's like an imaginary lid. I mean, these particles are evaporating. They want to go out, but as soon as they try to go out, they get bumped by the air molecules, and they won't be able to escape. Okay, is this clear?
Yeah.
I said this is called atmospheric pressure. The pressure that's exerted by the atmosphere. Now, your vapor must, if it wants to really escape, it must exert a pressure that's greater than the atmospheric pressure. Okay, Amal, is this clear?
Yeah.
Only then can the particles pass through the atmosphere and escape. Otherwise, they won't be able to. So vapor pressure must exceed the atmospheric pressure for evaporation to happen. Which is why you don't see uh, a lot of water evaporating in a cold environment. Why? Because the particles won't be very energetic, and they won't be able to sort of push through the atmosphere. Okay, is this clear?
Yeah. Okay.
So, this is all about vapor pressure. And we linked it with intermolecular forces. We just studied the properties that are dependent on intermolecular forces. Okay. So, Amal, we're going to continue with this in the,
Hmm.
in the next class then. Okay.
Okay, that's fine.
Okay, take care.
Take care.
Allah Hafiz.